What I want to talk about now is something very narrower than what Emmanuel talked about, on a particular thing that may be now very applicable also to many of the topological insulators or every topological word that you can hear around that have surface state. It has a bulk that supposedly is insulating and everything happens at the edges. And the reason that I'm very interested in the first topological insulator is the quantum Wall effect is that, as you will see as I go along, that we had a goal to observe statistics particularly in quasi-particles. And I must admit of a failure that lasted for about 10 years by now that we don't observe it. Okay, there are maybe a couple of groups that say they did, but we do not observe it. So what I want to give you a short introduction again. I know it will be a bit of a specific talk, and you might not be aware of all the details, but I think at least you'll get the melody out of it. That what we sort of believed in, or most of the community believed, how this simple system, in a way that has an insulating bulk and edges that are running current, is far from being the correct picture. Okay, so the way that, oops, why doesn't it work? It's supposed to switch. I tried it when I was sitting down. Well, let me take this out, put it back in. Oops, it works. Okay. So the semi-classical picture of propagation along the edge is showing here. We call it a skipping orbit, and we always define, and as you will see, I'll use this word, that there is a chirality, okay, that determines by the magnetic field. And then this is what we call usually an upstream, going in the chirality direction. And then you'll see things that are going also in the counter-propagating, which will be, this is downstream, and it will be upstream. Okay, so when you take this classical picture and you quantize it, then you get Landau levels. And then Landau levels, as they move toward the edge and the density goes down, okay, Landau levels curve up, and at some point, they cross the Fermi energy. And conduction can happen only near the Fermi energy, right? The density will drop down. You go, this particular one is filling factor 2 because there are 2 Landau levels below the Fermi level. And at the edge, this is the very simplistic picture of current transport. Okay? So what happens is that as you change the magnetic field, in this particular case, you have filling factor 1 because there is only 1 Landau level below the Fermi energy. If you lower down the magnetic field, then you have 2 of them. So we can play around on the number of edge channels or edge modes around the edge. Okay. So my main motivation in the research in this field was to look for this exchange statistic in the fractional quantum Wall regime. Because first of all, it's richer. I'll just give you a short reminder that in the 3-dimensional world we have bosons and we have fermions, and the statistic is well known. Okay. If you turn around a particle around the other one, then you change the wave function by pi. And the difference between boson and fermion is just when you exchange them. But when you go to the 2D regime, then you don't have to have pi or 2 pi. Then you have something that looks like this. And depending on the fraction, okay, most of the fractions that I'll talk about will be this Laflin-like fraction, which have an odd denominator. And then instead of having pi or 2 pi, we'll divide it in filling factor 1/3 by 3, filling factor 1/5 by 5. So this is very interesting, right? This exchange statistic is very amazing in a way, but it was never been shown before. So charge had been measured years ago, indeed, to show that this quasi-particle, imaginary particle, had a charge of 1/3 or 1/5 or 1/7. But no one could tackle until now the statistics itself. Okay? So what you see from this thing is, to see the statistics, you have to do interference. Well, there is other approaches too, like collisions of particles and looking across correlations, but you really want to have interference. And then you say, okay, what's the big deal? Let's just interfere. We know how to interfere electrons. Why can't we interfere these bullets of charges that really have charge, definite charge of 1/3 or whatever? Okay, and this interference was never observed, and I write here by us. So we started looking for it, and and when you look for it, you stumble about things that are unexpected. Okay, so what I want to talk to you about now is basically that the bulk's supposed to be insulating, right? But we find that it's very active. Okay, then there are all kind of energy modes moving through the structures, which we call neutral modes. Okay, and then the edge, rather than being this beautiful, nice edge, the density goes down, and even if it has some kinks at the edge or something like this, or flat regions, as Weizmann wrote many years ago, it totally reconstructs in a different way, somehow to lower energy due to correlation, Coulomb interaction, and exchange. And this is not really, it's not calculated. Okay, so you just observe it and let the theorist explain it. So basically, I'll tell you about this new picture that we see on the way to look for this statistic, which we don't see. Okay, so basically, what we believe in, okay, that's sort of the title of my talk, that the bulk is incompressible. Everybody says it. That's what you learn basically in every class. And then you say integer. Well, the integer quantum Hall effect. Why it's integer? It's like single particle, no interactions. Okay, this is what we believe too. Okay, and then there is this chiral propagation of current mode in the integer regime, in the propagating. I say propagating because down here I have counter-propagating. This we call downstream, and this is upstream for short. And we expect, and I will spend half of my talk on this so-called Hall conjugate states. These are the states that are between half and 1. So these Laughlin states are between 0 and half, or 1 and 1.5. And between half and the higher integer, we call them Hall conjugate states, because they are perceived to be like a full Landau level minus, a full Landau level plus Halls. And they totally behave differently. It was thought, okay? So we thought that they have also at least predicted that they should have counter-propagating modes. And it's okay that you don't understand what I say. I'll just show you. Okay. So first of all, I just want to show you that even I'll spend just a few minutes on the integer, on the simple integer, that it also has neutral mode inside. Okay. So how can I show you? Because later on I'll move to neutral mode in the fractional regime. But I want just to tell you that if you take integer quantum Hall effect, then you now introduce inter-channel interactions. Okay? So you have this edge mode I showed you before, moving in Finney factor 2, 2 channels going along the edge, everybody merely continuous, but once ignore that there is interaction between them. They are nearby, they are charged, why not? Okay? So let's look at this particular example of I don't know, can you see it? The resolution is not so great, but it's okay. It looks on my computer much better. Anyhow, suppose you have now Finney factor 2, and then you have these two edges going up, and then everything is chiral, and then they come from hot to cold, and from cold back to hot. And then you say, well, this is really a non-interacting system. Okay, so we solve it and we get Landau levels. And if you inject an electron here, the electron will keep moving here, and this guy, the other one, if I can inject to one Landau level versus the other, which is very easy to do today, then okay, this will be the propagation. But now, if I now add interaction in the system, okay, add interaction in the system, Landau level is not the eigen system. Okay, the eigenvalue of the system are not Landau level, because you have to add now interactions also. And then what happens is that if you solve it, and this is the paper by Berg and Yuval Oreg and Felix von Hoppen, that show that if it is all symmetric, I mean the two velocities are the same for any interaction, basically this is basically now the eigenvalue of the system. So now this, of course, the electron don't tunnel from one to another. It can happen too, but let's assume no tunneling, just interaction. So the interaction, we suggest that now you have sort of here E over 2, and E over 2 and minus E, I'm sorry, E over 2 and minus E over 2, E over 2 over 2. So basically you have now two modes. One of them will be, again, an electron moving around, and the other one will be neutral. You see E over 2 and E minus 2. Okay, so at the bottom, there is no net number of electrons because we didn't transfer any electrons there. So if you count down, you have 0 electrons here, okay? And at the top, you have the full electron. But this mode is propagating supposedly very fast, and this is the net neutral one, okay, propagates very, very slowly. And the velocity now is depending on the interaction. So the experiment that we just performed, and I just show you a couple of slides, this is not the main subject of my talk, is that we inject into one Landau level, okay, presumably getting this, but since these things, if you want to measure this and separate it from this, then it's high frequency, and it's not so simple to do. So what we did, we just looked at the lowest Landau level, okay? So the way that you inject it is using quantum point contact, okay? Quantum point contact is basically a little constriction that can move one edge or another one at will, okay? It's just a little, it's like a beam splitter, if you wish, okay? That you can vary the voltage on these gates, and you can vary the transmission coefficient. And we measure basically here what's happening only in this one by filtering it out, okay? So this is 0 net current, but hopefully we'll find some fluctuations here, okay? But you can understand it also semi-classically. It's not something very complicated because there is a mutual capacitance between these two guys, which is another word for interaction, okay? And then there are some high frequency fluctuation. If you put here an electron one at a time, then this current fluctuates at high frequency, okay? Depending on what's the current that you move through. And this high frequency is coupled here. Okay? So you have some frequency coupled here at high frequency because of these capacitors. And then we put here a quantum point contact that makes this very, very stochastic. And the stochasticity falls down the high frequency to something that we measure at low frequency. And that's all. That's the bottom line here. So if you do this experiment, and I don't want to elaborate on it, it's a very simple experiment. Indeed, you see that if you measure this cold edge, the one that we didn't inject current into, you see no current there, but you see noise. Okay? What you see here is noise. Okay? And I'll show you this curve. These units are a very funny unit, 10 to the minus 29 amperes per hertz, which is equivalent to thermal noise of a few millikelvin, let's say, in the quantum conductors. So this is basically, as you change the current and you change the transmission coefficient of this little guy, you have your noise that create bipartition. So the only reason to spend now a few minutes on this was to show that even if you work in the integer regime, interactions are important. There is also intra-mode interaction, not only inter-mode interaction. So the picture of integer quantum Hall effect, which I will not talk about here, is also not correct. This simplistic picture is not correct. Okay, so I want to go now to the main part with the fractional regime, which we spend a lot of time looking here for interference and failed. Okay, so first of all, the accepted view, and I keep doing it again and again, is that there is some localization in the bulk. I mean, there are electrons there, right? They didn't go anywhere, but they're totally localized, okay? And the edge of the integer quantum Hall effect is non-interacting, but I just dump it out. It's interacting, and many of our experiments in the group of moving from classical to quantum and vice versa rely on interaction between integer modes, okay? This is a very powerful tool, and there is a lot of interaction in the integer quantum Hall effect. Now, the edge itself, okay, in the fractional regime, okay, we know that it is really strongly interaction, and theorists solve it by using Latinger liquids, which is a very gross approximation, and it doesn't work. Everything that we try, we don't see any agreement with Latinger liquid, but it's a tool that theorists can use. And in this regime, there is abelian quasi-particle, which I'll talk about, and there is this also non-abelian quasi-particle, hopefully, not proven yet, in some even denominator fraction that's supposed to have the Majorana, which we are also aiming at this, okay? Okay, but what I want to talk about is just tell you a little bit about what we found out in these sort of trivial quantum states. Okay, so what you have here is that we always know the net number of states. The net number of states is is the forward minus the backward. And by measuring conductance, you never know. Because if you have 1/3, you don't know if you don't have another 2 of them. You might have 3 edges that are canceling each other, and you have only 1 at the end. But if you measure thermal conductance, which is much more difficult to do, which we are working now on, you can know the net number of states, because the thermal conductance will tell you how many one-dimensional edge channels are in the system. So in 1/3, you expect to get 1, which is also believed to be 1 always. It's a simple edge, right? The 2/3 is more complicated. I'll show you. It's supposed to be 0. You have 2 of them, at least predicted, okay? And the 3/5 is the other way around. You dump current into the downstream, but the heat goes in the opposite direction. So all these things are theorized. Okay, so let me just move on. This one I call the Hall conjugate, the Hall states, and this is the particle state. And I will talk in the rest of the talk a lot of this, but I'll start also with this. Okay, so first of all, this is the expected 1/3 state. It's the most robust fractional state, and we believe that we understand it. And the density is supposed to go down here, and there is, you see the density change, suggests that there is here electric field, and there is current going in the downstream direction. And we usually believe that it is gapped, okay, and the conductance is quantum conductance over 3, and the charge had been measured numerous amount of time to be E over 3. Okay, but however, the Hall conjugate state is more complicated, and already at the early 90s predicted by McDonald and Wen that it's supposed to do something like this, very funny stuff. It's supposed to have a full Landau 11 and holes of 1/3 inside, okay? So this is sort of what the bold prediction, okay? That the density, rather than going down to 0, it goes up and then down. And you see if it goes up and then down, that's what we call edge reconstruction. The edge reconstructs itself, the potential is reconstructed. And then here there is a minus 1/3 that goes upstream, okay? And there is a 1 that goes downstream, okay? That is the prediction. However, Ashuri at 1992 looked for this upstream 1/3 and didn't find it, okay? And this triggered basically also the conductance of something like this, supposed to be, if one think about it a little bit more than a second, you'd find it's supposed to be 4/3 and not 2/3. Anyhow, so Kane, Fisher, and Pulczynski, a couple of years later, predicted, and this was the belief until now, that there is now an interaction, and a disorder introduces between these two upstream and downstream tunneling, and there is interaction, because there is always disorder, okay? And you can just, the impurity can give you the momentum to go from one to another, and then you'll get eventually, you'll get 2/3 charge mode going down and a neutral going upstream. And the neutral is more difficult to measure because it's a neutral. It's just something that carries energy but no charge. You can think about it as dipoles moving around or something like this, okay? So the net number, again, remains here 0, and it remains here 0 if you count a neutral as a channel, okay? And indeed, the neutral is supposed to have the same thermal conductance as a charge mode, okay? Okay, so basically, of course, we start looking at this thing, okay? How do we find this neutral mode? And this we did a few years ago. And then I want to show you now why is it, again, very important? Because when we realize that neutral modes are supposed to be there, they could be, okay? Okay, this is the missing part because we always ignore it, but it could be a possible source of dephasing. Because if you have some energy currents going around, it could dephase my fractional charges. So we concentrated on it and we work on it for a long time by now, about 5 or 6 years, looking to try to understand this neutral mode, because if they are there and they are built into the system, there's no chance we'll find interference because they might just dephase me all the time. Okay, because they will grab energy for my quasi-particles, and as a result, they might just be dephased. Okay, so the way that I'm going to be now a bit more specific. Okay, so now how you do excite? Suppose they are there, you have to put some energy into it. How do you excite them? Okay, so if you have just a source, just a regular omiconduct source, and you inject current, and the current, this is the blue one here. This is, let's say, the propagating thing, the propagating current, and then this carries only half of the energy. It's simple. You just do an integral of dV and I and G, and you'll get here that half IV is here, and where's the other half of the power? It's at the backside of the contact. The back of the contact, even this beautiful experiment was done by a group of von Klitzing many years ago, okay, that they just had these are two omicontacts, and then they just dumped it into liquid helium, and they saw these two bubbles Okay, so this hot spot that were there evaporated basically the helium. So this was a poor man, beautiful experiment. Okay, so there is this heat generated at the backside, and since the neutral mode is going the opposite direction, upstream, this is my source of energy to drive the neutral mode. And the other way that we chose to do it later is to create this neutral mode by having a charged current, but rather than going into some contact and having a hot spot there, we came to a point contact here. And in the point contact here, there was some energy exchange between a cold channel and a hot channel, and you have a hot spot here too. So that these details are also important, okay? But we know that we create a neutral mode. The charge mode goes this way, the chirality is this way, and the neutral mode is supposed to go the other way, upstream. Okay, so I just want to show you now, so this is the way that we excite it. How do we measure it? So there were not only us, also the group of Amir Jacobi measured it. So you can have this neutral mode arriving at a point contact, and I draw it here as a dipole. And this dipole is being somehow partitioned in a way, so you can have sometimes hole, sometimes electron, and you will have, again, zero current, but noise. Or you can just throw it into just an OMI contact, and the OMI contact does the job for you, and you get also noise. Or you can go into a quantum dot, okay? And then you heat up this part versus this part, and then you'll have broadening of the resonance, or you'll have even a thermoelectric current. Anyhow, we measure it by measuring noise. Okay, so you will see a lot of noise measurement here. And this is a generic experiment, okay? So you see this is a point contact, and there are sources and ground. All of them are OMI contacts here. So you inject now from the source current. The current goes here. And here we generate now neutral mode if it exists indeed in this particular fraction. Because the particle, like, the 1/3, 2/5, all these things are not supposed to have neutral modes. They're simple fractions. And the 2/3, this whole one's supposed to have it, okay, because of whole conjugate state, because of this reconstruction. Okay, so now the neutral mode is supposed to go now, if it is there, it's supposed to go not in this direction, but in this direction. We have an amplifier here, and we're supposed to measure some noise coming in the amplifier if the neutral mode arrives there. And again, this particular one is the bulk. And I must tell you the truth that we had some by accident. We never suspected that the bulk is doing anything, but we had another amplifier sitting somewhere down here, totally by accident. In any case, let's just go to this. So this will detect the upstream neutral mode. This will detect the bulk if there is anything coming from the bulk. Okay, there is no current coming from the bulk for sure. This one we know. Rx6 is always equal 0. Rxy is quantized. There's no electrons moving through the bulk. Okay, but now let's go to the 2/3. Okay, so this is now just this number shows you the thermal conductance of an equivalent resistors with E square over H conductivity. So you see here that at the edge, you change the current and you have this neutral mode. So this is noise, and the noise can be, we know that there is some whole electron arriving. I cannot tell you how much energy they carry, but they carry current fluctuation. They decay with distance, they decay with temperature, but I'm not going to talk about all these details. But again, in the bulk, we see also noise. Okay, so this is the same, but no current. I didn't show you the conductance and the current here, but I see it's an order of magnitude less, so less energy goes through the bulk. And how does it go through the bulk? The bulk is incompressible, right? So how does this energy move through the bulk? I don't think it's totally understood. This is relatively new result. So somehow electrons are vibrating at some point with energy and they transfer by Coulomb interactions through the bulk. So the bulk is alive, okay? There is energy waves going through the bulk. But when we went down to 1/3, okay, that's exactly what I say. I'm sorry. This 2/3 you see in 3/5 and 1 1/3, 2 1/3, and also in 5/2. This is non-abelian state. So we have a bunch of measurement that shows where this neutral mode appear. But we never suspected until recently that they might appear also in Laughlin type state in the 1/3. So here is the 1/3 result that shows the same stuff. Okay, so again, you see less, the intensity is smaller, okay? You have sort of like lower spectral density. However, there is neutral mode here, okay, in the edge and in the bulk. So the 1/3 is not this simple one. The 1/3 is also probably reconstructed, okay? So this is totally unexpected, and of course, we see it in many other, not 1/3 only. So we believe that in every fraction under the sun, okay, there is neutral modes. There is every fraction, not in the integer. In the integer, we never see neutral mode. okay, you have a neutral mode. And maybe this is correlated somehow to the fact that we see beautiful interference for electrons, but we see none whatsoever with fractions. And then what I'm saying here, that I have no idea how the edge is reconstructed. I'm just saying that if you have neutral mode going in the other direction, in 1/3, then you must have one in the forward direction. You must have 3, okay? You know that the thermal conductance is 1, so if you add, you have to add them in pairs in the opposite direction. So somehow I just draw something here because I have no idea if this goes up and down, but the edge is reconstructed to allow neutral mode going upstream, okay? Okay, and also in the bulk, okay? So everything is alive. So now let me just tell you about, I think that I start a bit later, so another, okay. So I want to show, okay, so we have neutral mode all over. We understand maybe why we don't see interference. Can we conquer it somehow? In 1/3, there don't must. In 2/3, you have always 2. No matter what you do, you will have 2, because that's what theory says. In 1/3, it depends on detail. Maybe we'll have it, maybe not. Maybe if the edge will be very soft, we'll have it. If the edge will be very sharp, we won't have it, etc. But there was one more surprise that we did that I want to show you now in the 2/3 canonical Hall state. Okay, so when we measure, you have now the quantum point contact, and you have 2/3 filling factor, and then you are just pinching it out. You close it slowly. So usually you just go from 2/3 and you go down. But you see this, we have this funny, always in the 2/3 we have this plateau, okay? And this was published already in 2009. We had zero understanding how come the 2/3 has a 1/3. But the interpretation of this, rather than having a single mode, is that you have 2 1/3. So this is not what McDonald said and not what Ken and Fisher say. Okay, they said that you have 1 and minus 1/3. Okay, it goes 1, I'm sorry, 2/3 goes to 1 and down. Remember this picture. I'll repeat it again, okay? But this suggests that you sort of have a picture like this, okay? You have really 2 1/3, and now you fully reflect one, okay? And the other one goes through, so you have a plateau, okay? Until you start don't reflecting this one of 1/3 and 1/3, okay? So if in 2/3, if you have 2 plateaus, then you need 2 of them going in the opposite direction to have 0 net 1. But when we saw this, I said, okay, well, maybe it's this way, okay? But then there was another thing we don't understand. On the plateau, now, take a look at this, and maybe this is something not very clear to everybody. When you do something like this and you look on noise, what's the noise? You see, you put current from here, one edge, if this is the true case, goes continuously without any partitioning, right? And the other edge fully reflected. This particular one does not have any noise. And this was known already from 1990 or 1987, okay? When you have a full Fermi sea, okay, a full edge going in, it's noiseless. Even though electrons go one by one, but the wave function, the wave packets overlap each other so beautifully, 0 noise. The opticians would love to have photons that will have 0 noise, but they don't know how to do it because it's bosons and they bunch together, okay? Here, Pauli principle tells one electron to go after the other, and there is 0 noise. Always on a plateau, 0 noise. Okay? But here there is a plateau, okay? There is a plateau. On this plateau, you see the transmission of this little guy here is equal half. We sit on the plateau, and there is huge noise. So this is something we have no understanding whatsoever, okay? So why do we have noise on a plateau? So if there are 2 edges, why do we have noise on the plateau, okay? At unity transmission. Okay, so I'll show you now 2 very simple experiments, okay, that put some light on this. Okay? So first of all, we use, if you don't understand 1-point contact, put 2. Okay? So we have 2 of them. So you inject now from this source, you inject some current, you are sitting in the 2/3 regime, and this is long distance, 9 microns. so this edge comes around, and then in the single edge picture, not in the 2-edge, in the 2-edge state, in the 2-edge mode, and then part of it will be transmitted, part of it will be reflected and come to the other side. And what we do is that we keep this particular one, let's say, at some particular transmission, and we change this one, okay? So what you see here, the T2, as a matter of fact, T2 is half, the second one is half, on a plateau, you see? Okay, this is when T1 is 1. So the first point contact is fully open, it's not there. And the second one is at half, and then you get again this plateau. And don't be alarmed by all these resonances. This is very nice because it shows that you have very low temperatures. Every time you cool something to very low temperature, to the 10 millikelvin or so, then you have all these resonances because of impurity and resonant tunneling and things like this. So you have to live with it, okay? But you have a very nice plateau here. And now I'm going to start changing T1. And then, okay, it comes down. It looks like a single edge, okay? You go down. So basically what you have as you move down, that you have T1 times T2. What you expect, a single edge. Part of it is T1. You reflect it again, T2. So it's a multiplication. So this didn't give us any clue. But if you now, if we move now to adding another one, but making a very short distance, okay? So I'm showing now the same picture, but this is much shorter, okay? So this is now less than half a micron, okay? Then the story is totally different, okay? And what you have now, if you do this, the same experiment, again, the second one is half, and the first one here is totally open, and then you start now closing the first one. So you do 0.7, and then you do half, okay? Then you do half, and you get the same plateau. You see, it's not T1 times T2. It's very different, okay? When you go below half, then you get less. And let me just show you how can one explain it very easily, okay? So if you go now to this picture of the two edges, okay, so these are the two edges. So if this is open, both of them are one, then all these guys are going from here. The blue one are cold edge, because there's always stuff comes from the ground, right? Which are cold, not biased. So you have now, you see the two edges are coming over here, and I'm measuring all the time somewhere down here. Okay? So transmission is one. If now I go now that this is fully open, and this is half, this was the very first picture with the plateau, then this one will go here. This will be half of it will go through, and the outer one, or the inner one, if you wish, will not go in because it's half transmission. So only one edge, one third goes through. If now I go to T1 is equal 0.7, it's not a good choice of colors here, but you know that one will fully continue. This is the half, and the 0.7, the 0.2 above this will be partitioned, but again won't go in. And if I go now to half and half, one will be fully reflected, one will be fully transmitted. Okay? So this exactly explained and verified that the 2/3, rather than having one mode, it is really two modes. I'll finish in 2 minutes, okay? Okay, but still one mystery remains, okay? So we have now this, okay, and what I'm saying, if you go to long distance, if you now take this thing, I'm sorry, if you take now, if you take now this distance and go to many microns, then the red one and the blue one will equilibrate, okay? Here they don't have a chance to equilibrate, so the red remains hot and the cold and the blue remains cold, and they don't equilibrate, and that's the picture. But if you go for long distance, then carriers transfer from the red to the blue, and if this is one EV and one zero, then to be half an EV and half an EV. And that's the case. In this case, a lot of energy will be released, which are needed for in a second. Okay, so when we measure, okay, we understand this, but you can ask yourself before I move on, what is the likely reconstruction now? Okay, so the 2/3, we started with this, right? This was McDonald's picture, and this was Ashuri, didn't observe it, and later on Ken and Fisher came and said, come on, there is interaction between this, and it's really neutral upstream and 2/3 downstream. And that's what we believed until now, okay? But now we probably get something else. And this particular picture here is Yigal Meir from Beersheba, suggested this particular one, I think in 1994 or something like this, as a picture which is not Kane and Fisher picture, okay, or McDonald picture, and later on introducing all kind of the same story, interaction and etc. This now became now 2 1/3 down and 2 upstream neutral modes. Okay? Okay. So now what about this neutral mode issue? What is the business now? We have to come back and tell you why do I have now short noise on the plateau? Not short noise, noise. Noise on the plateau. Currentless noise on the plateau. So this is, I can just show you again that it's simple again because of neutral mode that must be there. Okay? So the picture is not very complicated. Let's go to again this canonical T equal half. So you have now this goes through, this is fully going here, and the amplifier sits here or here, doesn't matter, and you're not supposed to have any noise at all because everything you have transmission unity, okay? However, there is equilibration. You see the red slowly become bluish, and the bluish become more reddish, so there is some particle moving from here to here because of interaction, because of disorder basically, okay? And as they move, they release energy. So equilibration now, half an EV is dissipated in this process. Okay? And this is a source to excite neutral modes, which we know now that they exist. Okay? So this neutral mode is going now not in this direction, but in the opposite direction. Okay? These are counter-propagating. Same, whatever comes here happens here too. And when they come around, so now electrons generate neutral mode by releasing energy, and the neutral mode that comes here move along this two cold channel, and they dump their dipoles into electrons here and hole here, or electron here, stochastically. Okay? And basically, as you measure only the one here, the total of them, of course, will be zero because the same number of electrons in hole. But if you take only one channel here, you'll measure noise. And this was done, this was calculated also with a Fano factor by Yuval Geffen and his student, Jinon Park. Okay? So what I want now to tell you also, the same thing happens in 3/5. Another whole conjugate state. I'm not going to show you all the data, but you see short distance, you see all these things half. It's not half here, but it's 1/3 plateau. So this is, again, the whole picture of this all conjugate state totally changes. Okay, I think that I'll stop here. Okay? I think that what I wanted to leave you with now, that the integer is not an innocent integer with no interaction whatsoever. It's not sort of the single particle. And then upstream neutral mode exists. They are prevalent in every fraction, but not in the integer. Why there and not there? It's a different question. I don't know. Okay, why reconstruction takes place only in the fraction are not there? So we have edge reconstruction in all fractions that we measured at least. Okay, and there is a lot of energy propagation through the bulk. No current propagation through the bulk, but energy propagation. So this work really lasted already for the last 8 to 10 years or something like this. So this is not my group. Emmanuel, I'm not competing with you. My group is much smaller. But this is an integration of 10 years, people that were involved in it. Thanks very much.